talk about homework 2's problem 2. So now we have read down all the conditions here for probability of x1 equals to 0 is equals to 0.2 and x1 equals to 1 equals to 0.8. And also for the conditional probability, we also have the definition as, rewrite it as, for example, for sk plus 1 equals to 0 given by xk equals to 0. This one is equals to the intersection of xk plus 1 equals to 0 and sk equals to 0 divided by the probability of xk equals to 0. So let's start with our problem. For the first one, find the probability of x2 equals to 1. So for this one, we can divide it here by this one by two intersections. One is x2 equals to 1 with x1 equals to 0 plus the probability of the intersection of x2 equals to 1 with x1 equals to 1. And these two can be divided, can be applied for the conditional probabilities definition as the probability of x2 equals to 1 given by x1 equals to 0 times the probability of x1 equals to 0. And next one, similarly. Oh, this one is 1. So it is equals to 0.4 times 0.2 plus 0.7 times 0.8. It equals to 0.64. And for more space, if we can calculate p x2 equals to 0 at the same time, one way is as 1 minus p x2 plus 1. And the other way is also find the probability of intersection of x2 equals to 0, x1 equals to 0, and plus the probability of x2 equals to 0, x1 equals to 1. So basically, we can also write this into a matrix multiplication version. So it's probability of x2 equals to 1 equals to 0 and the probability of x2 equals to 1. They are equal to the probability of x2 equals to 0 given by x1 equals to 0. And similarly for the other. So this one is equal to probability of x1 equals to 1 and equals to 0 and x1 equals to 1, and this row vector times all the matrix here. So we can also have the version as the 0.2, 0.8 times 0.6, 0.4, 0.3, and 0.7 in this matrix. So similarly, we have the same way to calculate the other result. And this general form will be used in the following part. So for the second one, we need to find the probability of x3 equals to 1. So we have the So we can use the similar way. So x3 equals to 1 is equals to the probability of x3 equals to 1 with x2 equals 0 plus the probability of the intersection of x3 equals to 1 and equals to 1. And also it is equals to x3 equals to 1 given by x2 equals to 0 and times the probability of x2 equals to 0 plus similarly here. Similarly, we also from the previous problem, we also have this one. This x2 equals to 0 is also equals to px1 equals to 1. And now we also can find them in a general form of the problem. So as this row vector is equals to the probability of x2 equals to 1 and x2 equals 0 and x2 equals 1 times the conditional probability is set 0.6, 0.4, 0.3, 0.7. And this one is also equal to the probability of x1 equals to 0, x1 equals to 1 times 0.6, 0.4, 0.3, 0.7, and this one move here is as a square. So we can write a general form as px3 px k plus 1 equals to 0 and probability of px k plus 1 equals to 1. This row production is equal to probability of x1 equals to 0, x1 equals to 1 times to the power of k. So in this question, so k in this k plus 1 is 3 and k equals to 2. If we replace all the substitute all the values here given here, we can have the result. The result of the p r3 equals to 1 is equals to 0.592. Okay, for the third question, we should find the conditional probability of given by x1 equals to 0 of x1 equals to 0 given by x3 equals to 1. We already have the probability of x3 equals to 1 now, and we know that and this one given by the definition is equals to x3 equals to 1 with x1 equals to 0 divided by the probability of x3 equals to 1. And this one can be substituted as the probability of x3 equals 1 given by x1 equals to 0 times the probability of x1 equals to 0. And as x3 equals to 1. So we previously have the general formula as xk equals 0, xk equals 1, and equals to x1 equals 0, probability of x1 equals 0, 1 times all the conditional probabilities. Probably the matrix to the power of k. So if we given by, if we want to find this one, it is, we don't need to consider this part, this row vector, just for all the conditional properties together. So is equal to, so is 0.6, 0.4, 0.3, 0.7. If we to the power of 2 is equals to 0.48, 0.52, 0.39, and 0.61. And this is for the x3, 0 equals to 0, x1 equals to 0, and x3 equals to 1, given by x1 equals to 0. And this one is what we need here. So substitute the value together is 0.52 times 0.2 divided by 0.592 is equals to around 0.176. So for the final problem, as we have to find the elimination when close to infinity, goes to infinity of p x infinity to the fourth one, we have to find the elimination n to the n to infinity with the probability of pxn equals to 0. So for this one, if we use our general form, we can have probability of x infinity. It is equal to we can find elimination of n to the power to infinity as can we write as this way. So it is equals to, if we just consider the part inside the elimination, we can have the power. So this one is for the probability of 0.7.8 for the x1 equals to 0 at x1 equals 1, and all the other part 0.6, 0.4, 0.3, 0.7 to the power of n minus 1. And since this one is close to infinite and this one doesn't matter for doesn't affect the final result, so we move outside as 0.2, 0.8. And if we found elimination of n to the power of 6, 5, 26.4, 0.3, 0.7 to our n minus 1, which is close to the infinite. And if we use in this way, we can to find the elimination, we can find the diagram. The final one is equals to the linear of this one is 0.2.8 times 7/3 and 4/3. And for 7th, which is equals to 7, 3, and 7, 4. And so this one is for the elimination of Pn equals to 0, and this one is for limited of Pn equals to 1. And the 37 is our final result.